Hi everyone, this is pre-class video on module 2 symmetrical fault analysis. In this video I will be explaining how to solve the problems on symmetrical faults. Myself Dr. M.J. Chandrasekhar, Associate Professor, Department of EEE, SJB Institute of Technology. In the first two sessions on this module I explained about the analysis of transients on transmission lines and also the short circuit of a synchronous machine on no load, short circuit of a loaded synchronous machine. All these concepts along with selection of circuit breakers I explained. So, in this video I will be covering how to solve one or two problems on short circuit. Let us consider the first example, that is on symmetrical fault analysis. The first one is we will consider the problem which is having two generators connected in parallel, as you are seeing here. Two generators are connected in parallel to a LV voltage side of a 3-phase delta star transformer as shown in this figure 2.11. Generator 1 is rated at 5000 MV, that is you can write this in 3-phase basis. That is, the first generator is, I will write here. So, first generator rating is 50, let us write this in MVA, 50 MVA, and then 13.8 kilovolts, and it is having a generator 2 is 25 kV MVA, 13.8 I converted kVA into MVA. Each generator has a subtransient reactance of 25%, that is it is 25%, it is given, here is also 25% is given. So, that is X subtransient reactance of the generator. The transformer is rated 75 MVA, this is 75 MVA, and 13.8 delta, 13.8, this is 69 star. So, its function is to step up the voltage, and it is having a reactance of 10%, reactance is 10%. Before fault occurs, the voltage on the HT side of the transformer is 66 kilovolts. So, before HT side is 66 kilovolts. The transformer is not loaded and there is no circulating current between the generators. Find the subtransient current in each generator and the HT side of the transformer when 3-phase short circuit occurs at the HT terminals. Here is the fault. If the fault happens at the HT terminals of this transformer, then we have to find the currents. Select the base of 75 MVA and 69 kV on the HT side. So, that means this power system has two parts. One is the transformer divides. So, HT side base voltage is 69 kV and base power they have given that the 75 MVA, and in this problem it is required to find the base voltage on the LT side of this transformer. So, base voltage on LT side of the transformer is given by HT side value, that is HT side is 69 kV, it is given, multiplied by LT side voltage rating divided by HT side, that is 13.8 divided by 69, the rating of the transformer. So, 69 get cancelled. So, you will get base voltage here is 13.8 kV. So, this is how we can find the base voltage on the two parts of the power system. After that, we have to find the reactance in per unit, reactance in per unit. So, let us write the equivalent circuit of the reactance diagram for the given system. Two generators are in parallel here, two generators are in parallel. So, I will write that two generators in parallel this is one generator equivalent circuit. This is second generator reactance diagram, that is xg1, xg2, eg1, eg2, two generator, and then we have a transformer reactance, and then fault. So, this is the fault occurs. This is required to find the subtransient current. So, the values of reactances are taken 0.375, here 0.75. How to calculate that? Xg1 is equal to, on common base, Xg1 on rating into SB by SR into VR by VB whole square, VR by VB whole square. So, in the previous it is given that the reactance is 25%, SB is 75 MVA, and then this is 50 into VR by VB 13.8 whole square. This value comes to 0.375 per unit. Similarly, one can find xg2, this is also 0.25, SB is 75, SR is 25 for this, and VR by VB is same, VR by 13.8. So, the answer here is 0.75. So, you can find the transformer reactance as it is given, it is 10%, that is 0.1. So, this is how one can find the reactances of the individual power system components. And at the generator terminals, so the voltage Eg1 and Eg2 is So, actual value in the given problem is 66 ohm, but base value is 69. So, that is 0.9565 is the xg1 and xg2 values. Here Eg1 and Eg2 are considered to be in parallel, and both are identical in magnitude and phases, as there is no circulating current, it is given in the problem. The equivalent per unit reactance is they are in parallel. So, xg1 xg2 divided by xg1 plus xg2 is the equivalent value of reactance of the two generators. So, thereafter I will write the per unit reactance, total per unit reactance in the circuit. So, x value, so this xg1 is in parallel with xg2, and this is in series with 0.1. So, this value it comes to 0.35 per unit. So, now the current is voltage divided by the reactance. Voltage is 0.9565 in the previous slide and 0.35, then the total subtransient current is minus J 2.735 per unit. So, now let us find the actual value. So, actual value, so as we know, per unit value is equal to actual value divided by base value. So, this implies actual value is equal to per unit value multiplied by base value. So, per unit value is 2.735 into IB is 10 to the power of 3 SB divided by root 3 VB is the formula for finding the IB value. So, 10 to the power of 3 you write, SB remains same, that SB value is 75 divided by root 3. So, here the motor side base voltage is 69. So, if you solve, you will get the fault current in kilo amps, that is you will get 1.7 kilo amps, if you calculate. Now, it is told that it is required to find the values of the currents in the generator 1 and generator 2. So, here you can easily find, as you know the diagram here, the diagram. So, here the current which is coming out is Ig1 and here Ig2. So, use the branch current formula to find the currents. So, this I will explain in the next slide. As you know, here branch current formula is taken two generators, generator 1, generator 2, and then transformer reactance, and this is the fault I double dash we know, this transformer reactance we know, generator 2 reactance we know, generator 1 Eg1, Eg2. So, this is Ig2 and this is Ig1. So, the current Ig1 is minus main current I dash into opposite branch Xg2 divided by Xg1 plus Xg2. Similarly, Ig2 is equal to the current main current multiplied by opposite branch divided by sum of the branch reactances. So, by using these formulas we know the current, short circuit current, and we know the values of the reactances of the generator 1 and generator 2. By knowing this, we can find the subtransient currents which are flowing in generator 1 and 2. So, next let us consider one more example to understand how to calculate this using short circuit analysis. So, here for a radial network shown, the three phase fault occurs at F. The determination of finding the current it involves the predetermine the pre-fault reactance diagram for the given power system, and here the fault current it is required to find, and the line voltage at 11 kV bus bar under the fault condition. So, first we have to write the equivalent circuit of this. I will write the equivalent circuit, and we will see two generators are connected in parallel. So, generator 1, generator 2, they are connected in parallel, and it is with the transformer, then transmission line, one more transformer, and then we have a feeder. So, here the fault happens. Here the generator 1, generator 2, transformer 1, transformer 2, then transmission line and the feeder. We have to choose the base values in the generator side. So, here let us take SB as 10 MVA in the generator side, VB as 11 kV. Here this power system will have different parts from here to here, one part, two, second part, and all these are third part. Base values here it is 11 kV we have taken. Here base value it is required to find, and here also it is required to find. From the previous problems you can find the base voltages in the transmission line side. It comes to that is 33 kV after calculation, and here it comes to 6.6 kV. By knowing these base power and base voltages at each part of the power system, you can find the reactances of all the power system components except transmission line. Transmission line, if you take overhead line OH line 30 kilometers, how to find the per unit value? So, per unit value of this over a HV line is actual value 0.27 into plus 0.27 plus 0.27 0.27 plus J.36 per kilometer. How many kilometers? 30 kilometers. So, ohms per kilometer. How many kilometers? Kilometer. You multiply, you will get ohms. So, this is the actual value. So, per unit value is actual value divided by base value. ZB is VB square by SP. Here VB is known 33 kV, SB is also known. So, by knowing that you can find the per unit value of impedance of the overhead line. Similarly, this cable per unit value of impedance you can find. You can write all this in the reactance diagram as shown. By knowing this, you can find the short circuit current. So, here these two are in parallel, make it one like in the previous problem, all reactances, and here voltages value Eg1 is equal to Eg2 is equal to actual value divided by base value 11 by 11, that is 1 per unit. So, you can find the fault current. Fault current is equal to 1 per unit divided by this equivalent value of this plus all the reactances you can add. So, you will get the fault current. By knowing the fault current, one can find the current actual value. Actual value also you can find. That means you can find the fault current. By knowing the fault current, you can find the voltage at 11 kV. Voltage at 11 kV is equal to, so current multiplied by reactance. So, total equivalent value of reactance. Here the current value is 0.196 at an angle of minus 70.8 multiplied by reactance. Total reactance up to 11 kV. Up to 11 kV where the fault occurs, the total value is 4.46 at an angle of 67.98. So, if you multiply these two, you will get the voltage value. So, that comes around 0.874 per unit. Actual value means 11 kV, actual value means 0.874 into base value. Base value is 11. So, it comes to 9.614 kV. So, the actual value 11 kV is the rated voltage. Because of the fault, the current flows because of the voltage drop. So, to 0.96. This is how we can find the voltage at 11 kV bus bar. So, we have many problems like this. One can find the answers using the same concept. I hope this will be helpful.